Hi everyone, it's a pleasure to be giving this talk for this wonderful virtual workshop on Ricci and scalar curvature. I'd like to thank Christina Sormani for allowing us to present this ongoing work, and I'd like to thank all the other speakers for wonderful talks. And I will be talking about positive scalar curvature for open manifolds and the positive mass conjecture with bends. That stands for bad ends. And this is joint work with Ryan Unger and St. Yao. So the outline of the talk will involve some introductory material, classics in scalar curvature, talk about what I call the hereditary principle. I'll talk a little bit about some PSC obstructions originating in a paper of Shen Yao. I will mention and talk a little bit about the positive mass theorem, the Louisville theorem of Shen Yao from 1988. And finally, I will get to the positive mass conjecture with bends. And I'll talk about how this relates to this, and to this, and to this, and to this. Then I will go a little bit more into the details of what we've been working on. I'll present some results, and I'll describe and sketch the arguments in only minor details. And finally, I'll talk about some questions that one may ask in view of this discussion. Before getting started, I should mention something which has been mentioned before and will probably be mentioned again. A fundamental result in the field due to independent proofs by Shen Yao, which were for n is less or equal to 7 and Gromov-Clausen without any dimensional restrictions, is that the n-dimensional torus does not admit a PSC metric. Okay. More recently, a preprint of Shen Yao shows that actually the connect sum of a torus with any compact manifold, leaving the resultant orientable, does not admit a PSC metric. And here, among the results I'll be talking about is the following. If we take M to be the connect sum of a torus with some arbitrary non-compact manifold, then the resultant doesn't admit a PSC metric if n is equal to 3, or if n is between 4 and 7 and the manifold has bounded geometry. There's actually a more general version of this theorem that we have, but for the sake of the first slide, this is perhaps its simplest expression. And I'll describe the relevance of this to the positive mass conjecture with bends and the Louisville theorem of Shen Yao 88. So let's talk about the hereditary principle in the presence of positive scalar curvature. We start with a given closed manifold admitting a non-trivial one codimensional homology class, and we'll minimize area within that class. So here's a representative of the class. Here is our minimal surface arising from minimization of area. And because we've minimized, if we take our surface and we deform it in the direction normal to the surface, say, then because it's a local, well, in fact, here global minimum of area, then the second variation of area locally certainly is going to be non-negative. Phi and mu indicate that phi is a function defined on sigma and mu is the vector normal to sigma. The stability inequality, which is what results from computing the second variation, is the following. This is comes from demanding that it's a minimum. And then using the minimality and the Gauss equation, we can rewrite the Ricci term and obtain the following. But then since these terms occur with a good sign, you can put them on the right-hand side, and we get the following inequality. In fact, this should be a strict inequality, or we can keep it this way and then have a rigidity case in case of equality. But anyway, this implies that sigma, in fact, admits a PSC metric in its conformal class. So in other words, if MG is a closed manifold with PSC, then every closed two-sided stable minimal surface admits PSC, and hence the word hereditary. Now, a classic result in geometric measure theory reads as follows. Suppose MG is a compact manifold and we have a non-zero homology class alpha and Hn-1 with integer coefficients. And there exists an integral sum of smooth, oriented, minimal hypersurfaces that minimize volume amongst all smooth cycles in alpha. If we combine with the previous slide, then we get that M is a closed three manifold. If M is a closed three manifold such that no class in H2 can be represented by a disjoint union of spheres, then M doesn't admit a PSC metric, right? Because if it did, then we could minimize and obtain something that also admits PSC. But given that if it's oriented, right, and it's closed and it's PSC, it's a sphere. But we've just said that it can't be represented by disjoint union spheres. Let's switch gears a little bit and move on to asymptotically flat manifolds. So an asymptotically flat manifold is a manifold which looks a little like this. It's the union of manifolds which are outside a compact set, diffeomorphic to R3 minus a ball, and that have a coordinate system in which the metric falls off in comparison with the flat metric at some rate, which varies. And there are various definitions of asymptotically flat manifold. One can consider rougher metrics, etc. But working in the smooth category and for a given fall off, we can take this to be a kind of template definition. And then upon integrating certain components of the metric, certain derivative components of the metric against these two spheres, and then taking the limit as r goes to infinity, one defines the ADM mass. Now, although there is a coordinate dependence in this integral, it turns out this quantity on the left-hand side is coordinate independent, assuming a specific fall-off. But that wasn't so obvious initially, and in fact that was shown in '86 by Crucial and Bartnik independently. So the physicists Arnaud, Desser, and Misner came up with a definition of ADM mass and suggested that if the energy of the initial data of the manifold was sufficiently non-negative, then in fact the mass should be non-negative and should be zero if and only if the metric is flat. In Riemannian geometric terms, one looks at the scalar curvature, and the conjecture was that the ADM mass was non-negative, and in fact this was shown for the first time by Shane and Yao in '79. Witten gave a proof in '81 of a slightly more general theorem than the one stated, and since then there have been other proofs given, and the theorem's been generalized in various directions. For the purpose of this talk, the most relevant proof uses an idea of Locamp, which essentially compactifies the asymptotically flat manifold into something more workable. And the argument goes roughly as follows. Since M is the union of a compact set K with a finite number of asymptotic ends, Ni, First, we move to a nicer manifold, easier to work with. That involves various operators living on these manifolds. Then, after moving to a nicer version of such asymptotically flat manifolds, we can one-point compactify all but one end for which we assume, say, that the ADM mass is negative. And then using this negativity, we can produce a metric which is flat outside a compact set in this end. Once we've done that, we can identify the faces of a large cube in N1 and obtain a non-negative scalar curvature, but not exactly zero, on a compact manifold X, resulting from the one-point compactification of the other ends and the 3 torus. By a well-known result of Kasdan, we can deform to a strictly PSC metric, and then it becomes a question of ruling out such a metric on such a manifold, which we know from classic works in scalar curvature geometry. Higher dimensional version of this argument is really all about ruling out PSC on just a higher dimensional version of the torus. And the reason why this is difficult is because singularities occurring among minimizers, geometric measure theory minimizers, this is what I'm talking about, plague the above arguments. In particular, these minimizers tend to have singularities, and it makes the argument far more technical. Though Shane Yao in 2017 have given an argument. And then there's another argument of Lowcamp, which offers a totally different proof of this scalar curvature result. So just to summarize, Lowcamp's compactification looks a little like this. We start with some manifold with a finite number of ends. We suppose that the ADM mass is negative in one of these ends, say this one. And then we one-point compactify the other ends after having moved to a kind of nicer manifold, easier to work with, but keeping the scalar curvature bounds. And then using, moreover, the properties of this nicer manifold, in particular that it's conformally flat outside a compact set, we can find a metric which is actually flat outside a compact set in the chosen end. But then we can identify this this box and obtain a 3 torus connected sum with the other ends. And then the question is ruling out PSC on this manifold. And as I said, that's a problem in scalar curvature geometry. So this is the reduction of the positive mass theorem to a problem in scalar curvature geometry. And now let's move on to something slightly different, which will be the final motivation for the things to follow. A classical theorem of Louisville shows that any conformal map from an open set in Sn has a restriction of a conformal diffeomorphism from Sn to Sn, which is a composition of an isometry, dilatation, and inversion. Cooper in 49 shows that if Mg is simply connected, locally conformally flat, then there exists an immersion inducing the locally conformally flat structure on M by pullback, and that this map is unique up to conformal diffeomorphisms of Sn. So we have an immersion, and the question is now, when is phi, say, a diffeomorphism? When is it a diffeomorphism onto its image? In particular, when is it injective? And answering this question in '88, Shane Yao studied exactly this problem, inspired in part by Shane's resolution of the Yamabe problem, giving the last stone in a line of works by Aubin, Trudinger, and Yamabe. Shane Yao were able to prove that for non-negative scalar curvature in conformal maps, then phi is injective and hence a diffeomorphism onto its image under the following technical conditions. So either n is greater or equal to 7, in which case the argument goes through unharmed, or we have to assume the following conditions. In particular, in the 4-dimensional case, we have kind of these bounds on the scalar curvature and Ricci curvature. and otherwise abound on the scalar curvature for larger than 4. And then for larger or equal to 5, we need this Dirichlet eigenvalue to be strictly positive, where m is the hole in the cover of M. The details of these assumptions don't matter too much, but the point is that the theorem is believed to be true for n is greater or equal to 3, and without any of these hypotheses, 1 or 2. So the goal becomes to see whether we can remove these or improve upon these. The broad sketch of Schoen and Yau for this theorem is, again, reminiscent of Schoen's resolution of the Yamabe problem. One uses the minimal conformal Green's function with pole at P to define an energy function from M by assigning to P the ADM mass of the blow-up. So in other words, we take a manifold here, consider a point P. We know that Mg is a complete locally conforming flat, say, and then we look at the conformal Laplacian stemming from the formula one obtains from changing the scalar curvature after a conformal change. And we take the Green's function for this conformal Laplacian, called the conformal Green's function. And the conformal Green's function has a specific form on approach of P. In particular, it blows up. And because it blows up, we can use it as a conformal factor to transform this P neighborhood into an asymptotically flat end. And once we've done that, we can actually define an ADM mass in this end and then associate to M, which was a compact manifold, the ADM mass of the blow-up obtained by the conformal Green's function. Now, what they show is that E is actually positive everywhere if and only if the map is injected. So in order to show the Louisville Schoen-Yau theorem, it remains to show that E is always positive. So this leads directly to the positive mass conjecture with bends. In particular, Mg is a complete non-compact manifold with non-negative scalar curvature. We assume that one of the ends has an asymptotically flat structure, something that would be produced by the blow-up. And then the ADM mass of this end is non-negative. That's the conjecture. And if the mass is 0, then M has only one end and is flat. The validity of this conjecture would immediately imply the Liouville theorem in all dimensions without further restrictions. And that's the interest in wanting to prove that. The note is here that M is compact or non-compact, it doesn't matter. So in this picture in particular, I could have an end that would be going out here that doesn't have to be asymptotically flat. I should probably mention that this conjecture at this level of generality seems out of reach of current techniques. There's various ways to see that, but this can be a subject of discussion. But proving this at this level of generality, I certainly don't know how to do that. Just as a visual illustration, so we have the one asymptotically flat end, and then we just have an arbitrary manifold. I mean, this could be any geometry topology you like. Could be going down into a small neck, could be a cylinder, could be a sort of hyperbolic end, it could be just some repeating topology. I mean, it could be anything, arbitrary manifold. And then the question is the ADM mass of this end non-negative if we assume the scalar curvature is non-negative? So you might say, well, why don't I try and turn this into a compact manifold? The problem is that there's no clear way of doing that when these other ends are arbitrary. When these other ends are arbitrary, there's no obvious way, there's no obvious asymptotics, or there's no obvious thing like that that could allow you to do that. Nevertheless, you could motivate a kind of different conjecture, you could try and just say, okay, well, suppose Yn is a non-compact manifold, arbitrary non-compact manifold, then the connect sum with a torus doesn't admit a PSC metric. We know this is true if Yn is compact, but the non-compact case is fully open. In particular, if Lohkamp's procedure, if his compactification argument can be carried out to turn the wild manifold into one that looks like this, namely Y is some arbitrary non-compact manifold, but it's connects on with an n-torus, then the positive mass conjecture with bends will follow from the torus conjecture with bends. But in fact, this if is a great big if, because actually it's not clear how to do that at all, and that's something we can discuss in the questions. But it's not at all clear that could be done. However, I should say that, in fact, for the purpose of the Shenyao-Louisville theorem, one doesn't have to go to the positive mass conjecture with bends to get the Louisville theorem. So in particular, by kind of careful examination of the proof and Lohkamp's compactification, it turns out that the blow-up one obtains from the conformal Green's function is sufficiently nice that the Louisville theorem would follow from a torus conjecture. So that's the interest now in the torus conjecture. And the torus conjecture visually is a bit like this. So again, I have arbitrary ends. I don't know what they're doing. Just a non-compact manifold, could be really whatever. But I connect some with a torus, and then I say, well, this manifold doesn't admit a positive scalar curvature metric. So I think at this point, it's probably worth talking about what's actually known about PSC obstruction results, which manifolds admit and don't admit positive scalar curvature. And this is a sprawling literature with many beautiful papers and articles, but I'll have to only indicate those which are most relevant to what I'm talking about here. And basically, we'll start in the 60s with a T.S. Singer, their index theorem, and then the Lishner-Rowitz proof that the A-hat genus must vanish, given in 63. So I'm guessing this will be mentioned in the talks, but this is kind of the classic theorem. In 79 up to 85, Shen and Yao developed a totally different in spirit arguments to obstructions to PSC, which we saw at the beginning of the talk, namely codimension one homological classes being minimized, and stability inequalities, hereditary principle, and so forth. And Gromov-Larsen, in a series of landmark papers from 80 to 83, developed this index theoretic approach, and that really led to a number of further works in the whole literature in itself. In 92, Stefan Stoltz gave a proof of the Gromov-Larsen-Rosenberg conjecture, which was given in Gromov-Larsen and refined by Rosenberg in 83-86 for trivial pi 1. John Rowe developed a kind of index theory for non-compact manifolds and a coarse geometric approach to the subject, which was then developed and followed up by a number of other authors. That started in the late 80s up to today. Schick gave a counterexample to the Gromov-Larsen conjecture in 1998. We'll talk a little bit about that. Perelman's Ricci-Flowitz surgery arguments led to resolution of the Poincare conjecture, but also complete classification of PSC manifolds in the closed case. And Gromov's metric inequalities 2018 paper and his scalar curvature survey in 2019, I think, are wonderful references to delve in and contain many insights, and kind of summarizes this whole point of view of this minimal hypersurface methods versus the index theoretic methods. So as I said, for closed 3 manifolds, The work of Perelman implies a complete classification, and essentially we have a connected sum of spherical manifolds. These are manifolds which admit metric of positive constant sectional curvature and copies of S2 cross S1. For closed form manifolds, there is a result of Shane Yao in 1985 based on their work in 79 and 82, where they show that K pi 1 form manifolds do not admit PSC. I should note that this is a conjecture that's open for n is greater or equal to 5. As for the index theoretic type obstructions, as I said, there's the early 60s Tia Singer Lishner-Rowitz vanishing theorem. We have a compact spin manifold, PSC, then there are no harmonic spinners. That follows from the Lishner-Rowitz formula for the scalar curvature, which will be talked about in other talks and has already been mentioned by other speakers, and thus by the Tia Singer index theorem, the A hat genus must vanish. Developing these ideas and introducing the concept of enlargeability for spin manifolds, Gromov-Larsen obtained the following theorem. An enlargeable spin manifold does not admit a PSC metric, where enlargeable looks a little like this. So we start with a manifold and we look at finite covers of this manifold. And the idea is that we want to find maps onto the unit sphere that are epsilon contracting in length, right, in all directions, all lengths. And we want to find bigger and bigger covers such that these non-zero degree maps are epsilon contracting for smaller and smaller epsilon. And if we can do this for all epsilon, then we have an enlargeable manifold M. Originally, their definition was for spin manifolds, but that's been amended now, and one can also define something called area enlargeability. But in any case, that's for later. Still on the subject of closed manifolds, there remain a number of open problems in n equals 4 and n is greater or equal to 5. N equals 4 is a little special, and there are other scalar curvature obstruction results one can think about in that case. As for n is greater or equal to 5, the conjecture I mentioned before, Gromov-Larsen-Rosenberg, proposes that scalar curvature positive occurs if and only if a certain generalized so-called Rosenberg index vanishes. And as I said, in the simply connected case, Stolz solved this in 92, and one then obtains a very satisfactory characterization, namely, if M is not spin, then there is a PSC metric, and if M is spin, but this index vanishes, then one has PSC, if and only if. The conjecture, though, as shown by Schick, is false. In 1998, gave a counterexample. Now, moving on to the case of non-compact manifolds, using classic results in three-manifold topology and their methods of 79 and 82, Shane Yao obtained the following. So we have an open complete manifold, and then if the fundamental group contains a subgroup isomorphic to that of a surface with genus, non-zero genus, then M in fact admits no PSC metric. Bessières-Besson-Maillot in 2010 have a uniformly positive scalar curvature characterization in the category of bounded geometry, and there one obtains spherical manifolds and S2 cross S1s. Its proof is a Ricci flow with surgery, whereas this is totally minimal hypersurface in three-manifold topology. So in 3 dimensions, we have these very, very nice results. More generally, Gromov-Larsen obtained the following results. So again, we have an enlargeable spin manifold. Then how could you make something non-compact out of that? Well, you could cross it with R and high dimensional Rs. And this is what they obtained. So even if you cross it with R, there's no PSC. Cross it with R2, there's no uniform PSC. But as soon as you cross it with R3, then uniform PSC is now possible. Moreover, they show that if you have an area enlargeable non-compact complete spin manifold, then there's no uniform PSC metric. So area enlargeable here means that these epsilon contracting maps are contracting in area rather than length. So it's like a codimension 1 version of the length contraction. Without the spin assumption, I should say that this theorem of Gromov-Larsen is totally open, to my knowledge. One word or two about enlargeability. It can be defined, as I said, without the spin condition, but Sachin Schick have shown that essentially enlargeability is never interesting for non-compact manifolds. I mean, a complete non-compact manifold just is not enlargeable. That wasn't actually known. So that's kind of interesting, and motivated by the torus conjecture with bends that was mentioned before, one could consider that although we have this theorem of Sachin Schick telling us that non-compact isn't enlargeable, if we connect some with something enlargeable, then does the result admit a PSC metric? It's true in the case that M is spin and Y is compact. That was known from Gromov-Larsen's early work, but outside of these restrictions, it's just open. And finally, on the index theoretic side of the story for non-compact manifolds, as I said, Rowe proved an index theorem for non-compact manifolds, and Rowe and his collaborators subsequently developed a coarse geometric approach to the subject, and among other things, the following theorem, which says that if M is non-compact and spin, and D is a Dirac type operator whose associated curvature is uniformly positive outside a compact set, then the index is 0. For more along these lines, I suggest the paper, 2012 paper of Rowe, or the 2014 paper of Hanke Papa-Schick, which gives a beautifully clear proof of some of these coarse geometric aspects of the subject. In recent papers of Gromov, it's kind of mentioned often these two approaches to scalar curvature, index theory and minimal hypersurfaces. And one thing which is said is that index theoretic methods, they can be very powerful and prove things that minimal hypersurfaces can't, but at the same time, they need a spin assumption. And they also suffer from the following thing, that there are obstructions to PSC that are not visible by index theoretic methods. And the classic example, which is also the example for the counterexample for the Gromov-Larsen-Rosenberg conjecture, is that by doing surgery on the 5 torus, one can produce a manifold not admitting PSC. This is shown by Shane Yao type proof, but that has vanishing Rosenberg index. So in other words, the Gromov-Larsen-Rosenberg conjecture is false. At least the unstable version of it. There is a different version of it, which we can talk about. Coming back to Shane Yao 79, although not defined in that way, Gromov has recently put forward a definition which worked perfectly for this proof, and we call it class CN. So a closed manifold is a class CN if it admits a smooth map to the n-2 dimensional torus, such that for a generic point, the embedded surface represents an integral homology class, which is not in the image of the Hurwitz homomorphism. So this definition takes a while to unpack and think about, but basically what it does is that it kind of strengthens the Shane Yao argument, and basically shows that if M is a closed CN manifold of dimension 3 to 7, then M does not admit a PSC manifold. And that was already true by the arguments of Shane Yao 79. One of the main points about this definition is that if you're a closed codimension 1 hypersurface not homologous to 0 in Mn, then it's Cn-1 if M itself is Cn, right? So it has this inductive flavor, which is exactly what you do in the proof. In fact, that's why the definition is chosen to be this. So coming to the main theorem, so as I mentioned in the first slide, we have a theorem of this kind, and here is the kind of more substantive version of it. So suppose we have the following manifold. It's a connect sum of a Cn manifold and a non-compact manifold, and it's orientable. And then assume either n equals 3 or n is between 4 and 7, and M has either bounded geometry or is lambda rho contractible, then M does not in fact admit a complete PSC metric. And just to remind you of the definition of lambda rho contractible, that means that there exists constants lambda and rho such that all balls of radius less than rho are lambda Lipschitz contractible, i.e. lambda Lipschitz maps. It takes the ball and takes the ball across, say, at the point 0 being the original embeddings, and the maps at R being just a constant map. Lambda rho contractible can be thought of as a kind of lower order version of bounded geometry, or a kind of metric geometry version of bounds on the scalar curvature and Ricci curvature, but it's weaker. So as a warm-up to prove this theorem, I suggest we look at the punctured 2 torus. So the torus does not admit positive curvature. That is an even simpler result than the one I mentioned in the first slide, and we can see that by Gauss-Bonnet or other time proofs. One proof, one way to see it is that it contains infinitely many stable closed geodesics, but this is incompatible with the stability inequality and positive curvature once I wiggle this geodesic. And in fact, this argument motivated Shane and Yao's study of scalar curvature and minimal hypersurfaces. Recall the hereditary principle is about looking at stability inequality for these minimal hypersurfaces. In the non-compact case, we can also show that the punctured torus does not admit a complete metric with positive curvature. There's also various proofs to see this, but one way to see it is as follows. Suppose you have a gamma 1, which represents, which is a homotopically non-trivial curve in the 2 torus. And then I cut the punctured torus into, say, a compact exhaustion, and that I minimize in this class. Then I will get some curve, say gamma I for the ith exhaustion. But that as I go further up into the exhaustion, these curves might wiggle around and do whatever. But the idea is that if they go up to infinity and they become infinitely long, then in fact they're no longer minimizers, right? So by simple topological reasoning, the minimizing sequence would become too long if it left some compact set, say here. So there exists a closed limiting geodesic, and then the stability inequality will take care of the rest. So using exactly this picture, we can sketch a proof of the previous theorem that I mentioned. The first step is to set up the compact exhaustion. Then to minimize within a homology class given by the Cn definition for the compact manifold given by a member of the exhaustion. The key will be, of course, to prove the convergence of a sequence. If we have a situation like this, say, where we've done the compact exhaustion, say here, but then our minimizers are flying off to infinity, then they're not converging, and we'll be in trouble to try to prove anything. So proving convergence is key, and that will be done using a kind of homological anchor. I'll describe a little bit more on what that is, but in short, it comes from the connect sum structure and the definition of being Cn. Now it turns out that the compactness of sigma, which is the the surface to which this sequence converges, locally at least, fails in general. Although for n equals 3, standard results about minimal hypersurfaces show that actually sigma is compact. And then for n is between 4 and 7, the bounded geometry assumption implies that sigma is compact, or by Gromov's cone filling inequalities of 83 and his more recent arguments in metric inequalities, lambda rho contractibility is sufficient also to make sigma compact. Once sigma is compact, we can carry out the induction, and we're dry, we're home and dry. So that's a rough picture of the sket, right, of the exhaustion. So we exhaust the manifold. This is the torus, and then these are the bad ends, right, out here. We take this exhaustion, we deform the boundary to make it strictly mean convex, and then we minimize in the class given by Cn. So for the first exhaustion, maybe we get this surface. For the second, we get this surface. And then as we take the exhaustion to be larger and larger, we now are faced with the task of showing a kind of C infinity local convergence to sigma, which is anchored in K being a compact set, something like this. And the idea of anchoring is that basically the support of sigma cannot leave K. It cannot be fully outside K. So for instance, it's allowed to explore things outside K, as it does here, but there has to be some portion of it which is inside this compact set K. And K in particular contains a neighborhood of the surgery sphere, right, being something like here. Right, that's the surgery sphere. So as I said, sigma may be non-compact, that's this scenario, but sigma can also be compact, that's this scenario. And that will depend on the dimension. So problem 1, getting a convergent sequence, because as I said, the minimizers could fly off to infinity. And that is kind of resolved by the connect sum and the Cn definition. But then there's the issue of whether sigma is compact or non-compact. If it's compact, everything's fine. If it's non-compact, then we face a kind of important completeness issue. So what this says is that the hereditary principle mentioned earlier doesn't actually work so nicely in this setting. If sigma is a stable minimal hypersurface with trivial normal bundle, we have the stability inequality that I showed you before, and you can consider a kind of modified conformal Laplacian, which looks like this, and the stability inequality above will give us that the Dirichlet eigenvalue of L tilde is positive for all the bounded domains, and by Bartas theorem, there exists a smooth function on sigma satisfying L tilde u equals 0. And that's exactly what we wanted, namely that LU is positive, because then, of course, we have a conformal metric that has positive scalar curvature. However, there's a problem that was a kind of a subtlety that originally I had glazed over. U is an eigenfunction of L, and U may have a particular decay. And if U has a particular decay, then it's not clear that the conformal metric is actually complete, right? But if it's not complete, then all hell breaks loose, so to speak, because these theorems really hinge on completeness. And in particular, if U is not complete, we have no idea of why it's not complete, or in what sense is it not complete, what exactly is the fall off, etc. So without further understanding of these eigenfunctions, the conformal transformation doesn't it doesn't really help you that much. So that's a problem, and that's why when sigma is non-compact, you can't say very much. It does mean that you could look at these eigenfunctions and try and study them more carefully. That's something you could do, although it turns out that what you can show is highly sensitive on the geometry and your assumptions, and that statements of the generality mentioned are very, or at least we were not able to produce them. But that's something that one could look at in more detail, definitely. Anyway, as two corollaries of the main theorems sketched above, if M is the connect sum of X and Y, with X being in C3 and Y being non-compact, then M doesn't admit PSC. So that's nice. It's like a version of the Shane-Yao 82 theorem, except that it doesn't use any three-manifold topology. In a sense, however, it is slightly weaker because belonging in C3 actually implies that pi 1 contains a genus 1 surface subgroup or a greater. But the other direction doesn't seem likely. At least I can't think of how to prove the other direction. So I think the Shane-Yao theorem is, the 82 theorem is stronger, marginally stronger at least. But this theorem, this statement has the virtue of generalizing to higher dimensions. And in particular, gives us the Liouville theorem of Shane-Yao 88, which was proven without restrictions for n is greater or equal to 7. But now it's also true for n equals 3. And from n is between 4 and 6, assuming lambda rho contractibility, which is weaker than what was used in the 88 paper. Of course, the full theorem in full generality is still not resolved to our knowledge or with our methods. A quick word about what happens when sigma is non-compact. In that case, say we drop the contractibility assumption, then sigma can be non-compact. And if sigma is non-compact, but you have uniform PSC, then actually sigma cross S1 admits a complete PSC metric. Whether that's useful or not depends on whether the non-compact version of this conjecture is true. This conjecture was made by Rosenberg in 2000 in a survey article. The conjecture is not true for n equals 4, and it can be thought of as a kind of simpler version of the stabilized version of the Kromov-Larsen-Rosenberg conjecture, itself proposed by Rosenberg and Stoltz. But the conjecture reads that if M is closed connected, then M admits PSC if and only if M cross S1 does, kind of an S1 stability. Well, here, sigma cross S1 definitely does admit PSC metric, and so if the non-compact version of this conjecture is true, then sigma admits a PSC metric. And that would be great, because then one could start thinking about doing an induction. I think it's probably time to wrap up. I want to leave you with a couple of questions and conjectures. First of all, is lambda rho contractibility just a technical assumption? We're not sure about this. Perhaps there's a way to remove it. Perhaps the theorem is false without it, or some version of it. One question you could ask, kind of a more specific question, is do punctured CN manifolds admit PSC? We can't quite show this at present. So that would be an interesting question. One could even be more ambitious and ask, what about more complicated topologies? What if we remove S1 or knotted S1s or you know, all sorts of things? A basic question which you could ask is the connect sum area enlargeable if one of the summands is enlargeable? Say for Y non-compact, of course. That's not known to our knowledge. Is the theorem of Gromov-Larsen true without spin? So do area enlargeable manifolds admit uniform PSC metrics? That's not known. And of course, is the positive mass conjecture with bends true? And finally, although in a slightly different direction, is there an interesting algebraic avenue to follow, as there has been in the closed case with the Novikov conjecture? in view of these PSC results and PSC conjectures. But that's the end of my talk. I would like to thank you very much for your attention, and I will try my very best to tend to whatever questions. Thank you, and thank you again, Christina Sormani, for the opportunity to present.